Okay, this problem is going to look at the motion of a charged particle in the presence of an external electric field. So we have charged particle Q, positively charged, with a mass 4.12 times 10 to the minus 3 kilograms. We place that particle in a uniform electric field whose magnitude is 8.78 times 10 to the third newtons per coulomb. When we place that particle at rest, it experiences an acceleration of 6.14 times 10 to the third meters per second squared in the purely vertical direction. Negative, downward direction. So the question is, what's the direction of the electric field and what is the charge on Q? So in order for us to tackle the first question, we have to appreciate the motion of a charged particle. What happens? The force and acceleration, a charged particle field in the presence of an electric field. And we have a mini lecture in this playlist about how charged particles experience forces by electric fields. So if you haven't had a chance to check that out, you're not familiar with that concept, we're going to need that to answer this first part. So go back and review that video if necessary. In that video, we learned that charged particles, when positively charged, experience forces in the same direction as the electric field. So if I were to place a charged particle at rest, and that was the only force acting on it was the net external field, it would move and accelerate in the direction of that external field. Conversely, negative particles experience forces opposite the direction of the field. So if I were to place a negative charge in a uniform electric field and only considering the force acting by that field, if that was the only force acting on the particle, it would move in the direction opposite the field. So that's the first thing we want to keep in mind. If I have a charged particle Q and it was the only force acting, it would move in the direction of the field. But is this the only force acting on charged particle Q? Well, particle Q has a mass. So if it has a mass, we know gravity is also acting on this particle. So that means we have to take into consideration the net force, because it's the net force that causes the acceleration of that particle. So let's keep that in mind as we continue to explore this particular part of the question. So we know that the net force is in the negative y direction. How do we know that? Well, the acceleration is in the negative y direction. So if the acceleration is negative, that implies that the net force is negative. Accelerations and net forces are in the same direction. So we know that the net force is negative. We know that the force of gravity acts in the negative direction, vertical. Negative vertical direction. So this is negative vertical, this is negative vertical, keeping that in mind. Now, if the electric field was in the direction of any other direction but vertical, so if the electric field had a horizontal component to it, then the sum of the forces would also have to have a horizontal component. Since the acceleration of the particle is purely vertical, that means the net force acting on that particle is also purely vertical. I only have two forces acting on this particle, the electric field, so the electric force, and gravity, so the gravitational force. Since the gravitational force is purely vertical, the electric force has to be purely vertical. So that starts to get us answering this first question. We know that because the acceleration is purely vertical, there are no other components, there's no horizontal component, the electric field must be vertical. All right, so the question is it up or is it down? There's two possibilities. We could have the electric field being in the same direction as the force of gravity. So the electric force being in the same direction as the force of gravity. Or we could have the electric force being in the opposite direction as the force of gravity. So How are we going to distinguish between these two? Well, we can do that by looking at the value of the acceleration, the magnitude of the acceleration. Let's imagine for just a moment that the only force this particle felt was the force of gravity. So if I were to take this particle and just no electric field, just drop it in space, it would fall and it would accelerate in the direction of the force of gravity. What would be the acceleration? Well, if only gravity was acting, we know that that acceleration would be the acceleration due to gravity, 9.8 meters per second squared. So if only gravity was acting, it would accelerate at a rate of 9.8 meters per second squared. It's accelerating at a rate of 6.14 times 10 to the third meters per second squared. So the acceleration of Q is greater than the acceleration due to gravity, which means it's not just experiencing a force in the downward direction due to gravity, it must be experiencing another force in the downward direction. And so this is the situation we're in. It tells us that the electric force, because the acceleration is greater than that of gravity, it tells us that the electric force is in the downward direction. It's helping the force of gravity accelerate that object in the downward direction. If the electric force is in the downward direction and it is a positively charged particle experiencing that electric force, then we know the electric field is in the downward direction. So that's part one. The electric field is in the downward direction. All right, so we can use sort of our conceptual understanding of net forces, our conceptual understanding of how charged particles behave in the presence of electric fields to deduce that that electric force is in the downward direction, and therefore the electric field is in the downward direction. All right, so part two asks us how big is Q? And to determine how big Q is, we're going to utilize our understanding of how charge Q influences the electric force that it feels. So what do we want to remember? We want to remember that the force a charged particle feels in the presence of an electric field is equal to the magnitude of that charged particle times the magnitude of the electric field. Well, I know the electric field. I'm given that the problem. So if I were to be able to determine the magnitude of the electric force, then I could determine my value for Q. So to do that, we're going to do an explicit force analysis. So we're going to actually look at the forces now that we know the directions of the two forces. I'm going to do a force analysis to determine the value of Q. So in our force analysis process, we first identify that object Q. We've already talked about the two forces acting. We know that there's the force of gravity between particle Q and the Earth, and that's always in the downward direction. And we also know that there is an electric force between particle Q and the field, and that too is in the downward direction. So if I draw a free body diagram of my forces, of my object, I have the force of gravity and I have the electric force. Now I'm only dealing with forces in the vertical direction, so we'll go ahead and just analyze these two forces in the vertical direction. So we have force 1 and force 2. Force 1 is my electric force, so that's in the downward negative direction for my electric force. And force 2 is my force of gravity. That's minus mg, also in that downward direction. Applying Newton's second law, we know the sum of the forces is equal to the acceleration in the vertical direction. So I can add these two forces up. I have minus the electric force minus mg is equal to the mass times the acceleration. And I'm going to be explicit in my acceleration here. We know that acceleration is also in the negative direction. So I'm interested in the electric force. So I'm going to solve for the electric force. I have minus Fe equals minus Ma plus mg, bringing mg over. And then I'm going to multiply through that negative. I have Fe is equal to Ma minus mg. And therefore, my electric force is equal to my mass times the acceleration that the particle is experiencing minus the acceleration due to gravity. And so when I use my numbers that I'm provided, we find that the electric force has magnitude, we're determining the magnitude in this situation, has magnitude 25.25 newtons. So what do I do with that information? Well, we were going to use that to determine my value for Q. So if I wanted to figure out what Q is, I divide both sides by that electric field. It's going to give me Q. So 25.25 is my force divided by my electric field, which is 8.78 times 10 to the third. And I get a value for Q of 2.88 times 10 to the minus 3 coulombs. All right, 2.88 times 10 to the minus 3 coulombs. So, approaching both of these problems, both with that conceptual idea of how electric particles, charged particles, behave in electric fields, but also recognizing we have to appreciate this is the sum of the forces that cause the acceleration. So that force of gravity certainly is important. And then using our relationship for the magnitude of the force on a charged particle by an electric field to determine the value of that charge. All right, good job.